Hello. Good evening, everyone, and welcome to this very special lecture, the C.V. Vishveshwara Lecture of the International Center for Theoretical Sciences, ICTS, that I represent. We are very happy to do it this year in conjunction with Christ University. And I would like to thank Father Joseph, who, when I reached out to him and mentioned the prospect of Professor Roger Blandford giving this talk here, he was very supportive. He immediately connected us to Father Blesson, and I think it has been very nice. I believe many of you have met Roger in separate interaction earlier. The C.V. Vishveshwara Lecture is something that ICTS has instituted in honor of the late Professor Vishveshwara, who was a very important figure in astrophysics and cosmology. I won't go into the details of his biography, but he had most of his working life, in fact, was in Bangalore at the Raman Research Institute and the IIA. Many of you will probably recognize one of his lasting legacies, which is the Bangalore Planetarium, the Jawaharlal Nehru Planetarium, which was in a way his brainchild, and which continues to, I think, inspire many people, not only, of course, through the planetarium activities, but also through many science education programs. And we also hold our Copy with Curiosity CDs, ICTS's Copy with Curiosity CDs at the planetarium. So Professor Vishveshwara made a very seminal contribution to our understanding of black holes. In particular, what happens if you kind of knock a black hole. The black hole gets disturbed, it gets perturbed, it kind of starts oscillating a bit like a bell, but slowly, progressively relaxes back to its original state. And the precise way in which it does this is through a series of what are called quasi-normal modes or quasi-normal excitations, which describe how the black hole relaxes to equilibrium. And amazingly, this was work that he had done during his PhD and shortly after in the 1950s and 60s. It was discovered experimentally in the LIGO discovery of gravitational waves when two black holes merged, a binary black hole pair merged, and you could measure these, or you could see the signatures of these quasi-normal modes, these so-called ring-down modes. When the two black holes, after they merge, they gradually settle down into their final state. So this was imprinted on the wave signature that was detected, and that was a very special moment, of course, for Professor Vishveshwara, and I'll say a little bit about it in a moment. But in any case, to honor his legacy, ICTS had started this series some years ago. The inaugural lecture was given by Professor Kip Thorne, and in a way it is very fitting today to have Roger Blandford. Together, Roger and Kip have written this wonderful, already classic book on classical physics, modern classical physics, and which maybe many of you, if you are physics students, you will learn or have already seen. It's a very masterly survey of many different topics and with a lot of insights. So Kip Thorne gave the first lecture, and there have been a number of others. Last year we had Professor Satyaprakash, in fact, one of the people very active in the LIGO detection. And anyway, today we are very happy to have Roger here, and we'll later hear an introduction from Ajit. But before that, I would like to just have a small video recording by Professor Vishveshwara's daughter, Smita Vishveshwara. Professor Smita Vishveshwara is a condensed matter physicist at the University of Illinois Urbana-Champaign, and I think she's recorded a very short little message for us, and you'll hear.
Greetings to you all. My deep gratitude to Professor Rajesh Gopakumar and our other close ICTS colleagues, also on behalf of my mother, who's in the audience today, for having this ICTS series dedicated to my father and for having my presence here today. It really is a momentous occasion for me to be present here for this CVV lecture series today given by Professor Roger Blandford, and also to share with you another big event concerning my father directly related to the series. It is, in fact, after 12 years, he and I have brought to completion a book that we began writing 12 years ago when I was on sabbatical and I was visiting Bangalore. We began this as letters between father and daughter, sharing the wonders of relativity, the bread and butter of his work, and of quantum physics, the bread and butter of my work. And we decided that these were fields, revolutionary fields that we loved so much and that we wanted to share not only with each other, but perhaps as a book. And so after 12 years, I have brought this to completion also on behalf of my father, and it's to be released, in fact, mid-January. This is now late December for me when I'm making this recording, and so by the time you are seeing this, it will be out in publication.
Yeah, so that was Smita, as you heard. There's a new book which I believe has just been released last Wednesday, and we will actually have Professor Vishveshwara, Smita Vishveshwara, come and give a reading from her book about both these revolutions that the father and the daughter were writing about. But right now, this is the year of the quantum, 2025. We are celebrating the centenary of quantum mechanics, the second revolution that was talked about over there. So I'll just give a small preview of what Smita has written about this, and just to set a certain context. She writes in the preface to her book, in February 2016, one of the greatest physics discoveries of the century came to light, the detection of gravitational waves from two black holes a billion light years away, spiraling into each other and merging, announced by the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo collaboration. Predicted by Einstein 100 years earlier, the detection was a colossal human feat. Gravitational physics and black hole studies experienced a spectacular new heyday. The discovery opened a new window into the cosmos. And this, so she goes on to talk about 2016, the year in which this happens. And on the personal front, the year's happenings were equally eventful. But it also so happened that things changed in April of the following year when Vishu fell critically ill and was hospitalized, and he breathed his last in January 2017 till the end. As long as life throbbed within him, his love remained unwavering, and his mind remained as vibrant, mirthful, alert, and youthful as ever. And in fact, one of the last talks that he gave was at ICTS, just after the discovery of the gravitational waves, when we had a small little event there to celebrate it. So in any case, it's very special to have this lecture series in honor of him, and I'm very grateful to Professor Saraswati Vishveshwara, who is here with us today, for joining us also for this occasion. And now I would like to invite Professor Saraswati Vishveshwara to hand over a small memento to the speaker, Professor Roger Blandford. And now Professor Ajit, P. Ajit from ICTS will introduce the speaker, Roger Brown.
Good evening. It's a great pleasure to introduce today's speaker, Professor Roger Blandford. He's an astrophysicist, as you know, who is widely recognized for his contributions to different aspects of astrophysics, including the study of black holes, particle acceleration in astrophysics, and gravitational lensing. And his many achievements include the discovery of how energy is extracted from rotating black holes, which is now called as the Blandford's Banach mechanism. He is the founding director of the Kavli Institute for Particle Astrophysics and Cosmology at Stanford. Among the many services that he rendered to science, and he chaired the US National Academy of Sciences Decadal Survey for astronomy and astrophysics, the previous one, 2008 and 2010, which in some sense sets the stage for astronomy research globally over the next decade. Professor Blandford is widely recognized for his pioneering theoretical work as well as for his contributions to science at large. He has received numerous awards and fellowships of various academies of science across the world, which I'm not going to enumerate. He's an inspiring teacher, as you would see now. Professor Blandford recently co-authored a textbook with Kip Thorne, the modern classical physics, which has already become a modern classic over the last few years. But today he is going to talk about the quantum, about the quantum in astrophysics. Professor Blandford.
Well, thank you very much, Ajit, and everyone here for the very kind invitation to come here. I enjoyed myself hugely in Bangalore, and 20. Sorry? Oh, so I should stand here then. I was told, oh, okay, yes. Okay, okay, all right. Okay, I'm enjoying myself hugely, and it's a very great honor for me to be delivering this lecture. I had the privilege of meeting Professor Vishveshwara, I think must be in around about 2008, I think it was, and I very much enjoyed that, and I'm also very honored to be following the distinguished lectures in front of me, including, as you just mentioned, my colleague and friend Kip Thorne. I feel a bit of a fraud as we wrote this book on classical physics, here talking about quantum astrophysics and attending a wonderful conference at ICTS on the quantum century. So we wrote this book on classical physics, and Kip Thorne, as you probably know, is most famous for being the instigator of the movie Interstellar. How many of you seen that? Oh, it's quite a lot. Okay, so it was. I'm a great fan, and he's great, and he's a very generous man. We wrote this book, and I couldn't bring a copy with me; it's too heavy. But he did give me the movie rights to the book. He's also somewhat well known for having won the Nobel Prize for being one of the instigators of the LIGO project and doing much of the theory for the detection of gravitational waves. I have a little more to say about that. And explain some of the things that we were talking about earlier in the week at ICTS. And I've called this for quantum astrophysics. The phrase I've never heard used before, but my intent is to take, if you like, the symbiosis or the intersection between quantum physics and astronomy and just pull out some of the things, the many things that have happened in that area over the past century. And then I'm going to, this time, I'm going to, at this time, at the end, I will give you 3 topics that I personally am excited about at the moment and am working on right now, and they all have aspects, different aspects, that I think are strongly quantum mechanical as well as being of interest in astronomy. So perhaps by way of introduction, I should make this distinction and say a little bit, I do space. Is that visible? Okay, if you can see it, I can see it very well. Okay, classical physics, as I'm sure most of you in the audience know, was a glorious achievement. It had many begetters, obviously famously Newton, but many more people after him. I won't list them. And it was really concerned with matters like the motion of apples and the moon and planets on the one hand, the motion of something like the cricket ball here by one of my heroes, and that required a force which gave you a motion. In fact, more than one force because there's air resistance there. And Newtonian physics told us how to describe that motion in a quantitative way. It can also be used in geophysics for the understanding giant mountains like this one here. It can be used in the oceans for oceanography. It can be used in thermodynamics. This is all classical physics. And historically, of course, a lot of it was concerned with the business of power and so on. That's true in astrophysics. And it can also be used in optics. And here's a telescope, Wilson telescope. And the way forward, as has been the case in a lot of the physical sciences, is through a series of prescriptions. In this case, here are 2 equations. I'm not going to identify them or interpret them. I just put them there as indications of the way we actually think about solving problems involving these and countless other applications. And nowadays, in the old days, we would do this using mathematics of the sort you can find in a textbook. Nowadays, increasingly, this is done with computation. And most engineering, and indeed quite a lot of physics, is adequately described by the classical physics of mechanics, of electromagnetism, of thermodynamics, and so on. However, in the 19th century, it became clear that classical physics, despite its glorious successes, was not sufficient to describe all that was being discovered. The evidence appeared in many different ways that materials were made up out of atoms, individual particles, specifically initially the electron, were discovered, and people started to worry about light, about radiation, and to try and understand its spectrum, and they found that a naive application of general principles of classical physics was insufficient. And instead, starting at the end of the 19th century, involving Planck, Einstein, Bohr, and many others, who were slowly developed a complementary way of thinking about matter and light and all that their interactions, that became known as quantum mechanics. And what we've been celebrating this in ICTS is a centenary of a series of major advances in the understanding of quantum mechanics that happened loosely around 100 years ago. You can say some of them happened a year or so earlier, a few of them happened a year or so later, but in 3 or 4 years, a group of mostly very young people, in their mid-20s, changed our view of physics and by extension of much of the rest of science. And this was quantum physics. They discovered, and I cannot go through all of this at all, but they discovered that atoms had an amazing structure. In some ways, the original description of them, they were like planets orbiting a sun. There was a small nucleus, and there was a planet, many planets orbiting around them called electrons. That was an initial description. They discovered that light, instead of being sort of a continuous thing like a flowing river or something, was indeed composed itself of particles like electrons, and those are called photons. This was one of the things that Einstein argued for very successfully. And very quickly, particularly 100 years ago, the formalism developed, again through a series of equations, which I'm not going to interpret, I'll just write them down here. And that has been going on ever since over this century. As they went from the large-scale macroscopic world around us down to the atoms and the molecules that are composed of atoms, they looked inside the nucleus, and they found that that itself was composite. It was made up of smaller particles. They found, I'm going to call out a few of them here because they're going to come up later in the story. They found a series of particles here, which are called, we're going to call them quarks and leptons and bosons. And boson, I should remind you, is named after one of the pioneers of understanding this sort of physics, Professor Bose here, and from India. And they discovered that particles had opposite particles called antiparticles. In the case of an electron, it had an antiparticle which became known as a positron eventually. And they were very similar, except the charge, the electrical charge associated with an electron, is the opposite of that associated with a positron, and so on for these other particles. They found that the nucleus of this atom was made up of neutrons and protons. And then they found that the neutrons and protons themselves were made up of particles called quarks, the more fundamental particles here, and they were coupled together by particles that essentially glued them together, and we could call those, they were called gluons. And this pattern here, which I'm nowhere going to even start to explain, is one that has been corroborated without any doubt so many times and built upon to understand other features of the basic physics at the smallest scale. The quantum mechanics is essentially how to describe physics on the very smallest scale. And I want you to hold that thought in your head because we're going to finish off with talking about that again. As I say, we can take 3 of these quarks to make a proton, one of the constituents of the atomic nucleus. We can take 2 of them to make a different type of particle, which I'm going to call a meson. And there are ions which you can, one of them is called here, that's called, for example, the pion and the kaon. Again, that's going to come up. And then there's a different type of particle which is shown here, which is the muon. So I'm just drawing attention to those here, and they'll come up again. one of the features of the quantum description of the world is that particle, like an electron, is not just like one of those cricket balls. It has a duality. It has two aspects to its character. It can be thought of as a wave and a particle. And the way we think about it nowadays, it isn't just it's one or the other. It is described by something which can be expressed in some instances as showing more its wave-like character, and something that shows more its particle-like character. If we look at it in an atom, then we can say, let's take an atom, this is in this case it's hydrogen, and we find that the electron there can exist in a series of states, a series of organizations, and with probabilities that are shown schematically in orange here, around the nucleus, the tiny thing of the nucleus, the tiny thing, 5 orders of magnitude smaller in the center of this. And then this is the distribution of where you might find the electron orbiting, one electron orbiting that. And if the electron has a lot of energy, it'll be, say, in this state. If it doesn't have so much energy, it'll be in that state. And what you find is that an electron, if you started it in that state, in a given time, it will change perhaps to that state, perhaps into another state. And as it does so, it will lose energy. And energy is conserved, and the energy appears in this instance as a photon, as one of these particles of light. So that was a remarkable change in thinking about physics. And although I'm a co-author of a book on classical physics, I want to say completely that quantum mechanics is the fundamental physics, and classical physics emerges from that, from a limit when this sort of structure can be averaged over. That doesn't mean to say that classical physics is irrelevant, certainly not, but it does mean that because it's often the tool that one uses to solve most engineering problems and so on, but quantum mechanics is the fundamental thing, and increasingly it's a part of our life. Here. So this has been a century of quantum mechanics, and one of the things that has happened is not so much all of this theory associated with physics textbooks or whatever. It's been the application of quantum mechanics to the world around us. And essentially, we started off with pictures of steam engines and things like that. Now we have pictures of pocket calculators, of drugs, down here, of materials that are subtly engineered for specific purposes. We have a picture of a embryonic, if we might say, quantum computer here. This is one that uses, in a very deep way, the principles of quantum mechanics to do computing in a very different way done there. And so, in countless ways, many of which you may not be conscious of, quantum mechanics has created the world around us. And so these are all applications, if you like, of quantum mechanics. And it's not as though it's just a theory. It's a theory that we understand exquisitely well in physics, in chemistry, in biology, in various types of engineering, and so on. And we can apply with confidence to make new devices, to solve new problems, and so on. I said it was the century of the quantum. Excuse me. It's also been the century of astronomy. And astronomy, of course, began with a fixation on optical telescopes used to explore the heavens. And glad to hear that Professor Vishveshwara founded the Bangalore Planetarium, because even somebody who works on general relativity and astrophysics always gets the kick from looking at the night sky with a telescope. And when I get time and I take my own telescope out and look at it. So I'm still filled with the marvel of looking at the sky, but this has been a century in which making catalogues and looking with an optical telescope has been completely overwhelmed by looking with a whole range of new telescopes. Here's Hubble telescope, here's James Webb Space Telescope in the infrared, you've probably heard of this, DMRT, an Indian radio telescope. Here's the radio telescope that was used to make this image of a black hole. It's a combination of telescopes, radio dishes all around the world. Here's AstroSat, an Indian X-ray telescope. Here's Fermi Gamma Ray Space Telescope. And here are ones that I'll say a little bit more about. Here's an underground neutrino telescope. I could perhaps have called out here. I forgot to call out. Let me go back. My particles here. I was just going to call out the neutrinos up here, and their fundamental particles too. And we'll have a little bit more to say about those. Here's one that is a large telescope, and it's involved with telescope. Here's the LIGO telescope, and this is a Chinese telescope that looks at very high energy photons called gamma ray. So all of these have been engines of discovery and have completely transformed our understanding of the universe. Just to drive home that point, here is a representation of what we call the spectrum of radiation, of electromagnetic radiation, and we now know things like radio waves and gamma rays and optical radiation and ultraviolet and infrared radiation, all part of the same, they're all the same photons, but they are photons with different wavelengths and different frequencies, because they all travel at the same speed, the speed of light. And if we imagine replacing the frequencies of those photons by analog frequencies associated with a series of pianos, and obviously they would have to go down, then we're going to need 10 grand pianos worth of spectrum to see the whole electromagnetic spectrum. And what astronomers used to use was optical observation, using 1 octave of the spectrum, 1 octave, a power of 2 in the frequency, from red all the way to violet. If you like, that's what they used the old-fashioned way. Now we've got all of this, 70 or so of there. And in addition, they have cosmic rays they can look at. And cosmic rays are not photons, they are charged particles, protons and the nuclei of atoms that hit the Earth all the time. We'll say more about those in a while. And they are messengers of the cosmos. They teach us about the world around. In addition, we now have gravitational radiation, as observed by LIGO, and we hope very soon. LIGO's new outstation, which is going to be out in Mumbai. That's to be a very exciting development in this business. And then neutrinos. I mentioned the neutrinos. I'll say a little bit more about these too. They are messengers. And so we've got roughly about 140 or 150 octaves worth of spectrum to look at in different forms, in complementary ways. And that can help us understand the world around. So what I'm looking at here is the sort of intersection, the interface, if you like, between the century of physics and the century of astronomy, and I'm going to call this quantum astrophysics. And I've tried to organize this a little bit by the atomic physics of astronomy, the nuclear physics of astronomy, the particle physics of astronomy, and a little bit about cosmology. So obviously this is a huge topic, and I can only just give you a glimpse of what there is happening, what has happened, and what is happening. So let's talk about the century of atomic astrophysics. Here are three Indian pioneers of this science, Saha, Chandrasekhar, Mohammed, and many more. And one of the big accomplishments was to understand the light that you saw in stars like the sun. Not just the sun, one looks at all the other stars and the sky, and you find, as was first realized by Fraunhofer, that if you look at the light that comes with different wavelengths, going all the way from the short wavelength on the blue side to the longer wavelengths on the red side, then there were a series of dark lines in it. And those dark lines correspond to the light taken out by atoms. And I emphasize that these atoms were involved with transitions that had very specific energies and very specific frequencies and wavelengths associated with the light that was either emitted or absorbed. In this case, it's absorbed. So we get these dark lines to form. And many astronomers spent a lot of time heroically observing all the stars and organizing and cataloging the line. They knew that they were related to the different elements that were present in those stars, and especially Saha's contribution to the temperature that was involved. And as a result of the application of the principles of quantum mechanics, this organization got translated into a precise physics interpretation. And so you can say this star has a lot of calcium in, that star has a lot of strontium in it, and so on and so forth. And that organization led to the stars being organized in a way that was very physics-oriented on a diagram that essentially is think of this as a plot of the temperature of the star going from red to blue, from low temperature to high temperature, and of its power or its luminosity, which is what astronomers say, low luminosity to high luminosity. And most of the stars, like our sun, spend most of their life in this region here. The high mass stars are up here, sun's about there, low mass stars are down there. The high mass stars live fast and die young. They live perhaps only millions of years. The low mass stars live for trillions of years. The sun is good for about 10 billion years. After that, they can evolve in a way that we now understand, and all of this depends on applying quantum mechanics to the interiors of stars. Our sun will end up as a white dwarf. Other ones will go through supernova explosion and can give us neutron stars and black holes. If we look at what's been happening recently, as I say, I'm just going to give you just a glimpse of a huge progress that's happened. Here, just three that are personal to me, if you like. I mentioned that there's the interest in I mentioned talking to the students today, and one of the things of interest is to understand exoplanets. These are the planets that are now found in abundance around other stars. We didn't know this 30 years ago. We now know that most stars have lots of planets. They all behave in idiosyncratic ways, and not just like the ones in our solar system. And of course, people are looking there for evidence for life, biosignatures, seeing if they can see if there's a place where life might have originated there. There are many claims, of course, but the first step along that road is to understand the composition of those exoplanets, which you can see either directly in emission or through looking at the light being absorbed by those atmospheres as it comes from a companion star through the planetary atmosphere. And so this is now a very lot of being learned, especially with James Webb's telescope about. We can also see exotic chemistry out in interstellar space. And these are molecules that you won't find on Earth at all. Here's an aromatic, sort of carbon-based, like hydrocarbon molecule that's out there in outer space. And you only can make this identification because you confidently can calculate what the spectrum should look like. And here's one that will come back later in the talk. Throw it out here. It's the first evidence in interstellar space of a molecule we call as being chiral. I won't give its name. It's just chiral, and what that means is that if I make a model of that molecule by arranging spheres together, then if I looked in a mirror, it would be different. Simple molecules like carbon dioxide or water are not like that, but this is one that's sufficiently complicated that if I looked in the mirror, it's distinguishable. We call that a chiral molecule. I'll return to this point later. If I go now, transition into nuclear astrophysics, this is the physics of nuclei in the centers of atoms, but usually without the electrons around them, so they're just bare nuclei, some roughly 5 orders of magnitude smaller, 100,000 times, smaller than the atoms. Then applying the principles of nuclear physics, which were learned from doing experiments on laboratories, we now understand how stars shine. We understand that they are powered not by the release of gravitational energy or chemical energy, but through nuclear power. And here's just one little bit of the reaction sequence. I'm not going to go through it. That takes hydrogen into helium, and when you take the hydrogen in the center of the sun and change it into helium through nuclear reactions, you release energy, and it's so much energy you release that it can cause the sun to shine for roughly, as I said, 10 billion years. And it works in different ways, in different stars, but that is what we need. Many astrophysicists and physicists were very curious about where the chemical elements come from, the stardust, if you like, that we are made of. One of the discoveries that was made was that it was not possible to make them all in the very early universe. The universe gave us hydrogen and helium and not much else beside. So you had to make it in stars. But how? Well, it turns out there are several mechanisms at work. One is massive stars can burn hydrogen to helium, and then in a wonderful piece of physics detective work, it was found out how to convert helium, which has 4 particles in it, into carbon, which has 12 particles in it. It was known that just having 3 helium nuclei come together and make a carbon atom, the carbon nucleus was inadequate. And the way it actually happened is that 2 helium nuclei come together, make a beryllium nucleus, which would normally decay very fast. But there is a special excited state of the carbon atom, this was predicted, and it allows sufficiently often another helium nucleus to come together and meet the beryllium nucleus and make carbon atom, and it does it sufficiently often to make carbon. And then you can add another helium nucleus to make oxygen, neon, and so on, and you build up a lot of the chemical elements that way through burning of nuclear fuel inside massive stars. That theory was all worked out. Then what happens is after you've exhausted all your nuclear fuel with a massive star, then the star will collapse. And that collapsing star will undergo an explosion, which we now call a supernova. That supernova is a source of many of the heavier elements around. The ones that are more heavy than iron, which is really as far as you can get with those reactions inside regular stars. And through, as I say, a piece of physics come astronomy detective work, a story was put together in the 1950s that is called created essentially nuclear astrophysics, and it described how the elements came together to give us all the elements we see around us and the foundation of chemistry and biology and the rest. Much else was discovered. I said that when a star ran out of its nuclear fuel, it would collapse. Most stars that are in that state, if it runs out of nuclear fuel in that, massive stars more massive actually than 8 times the mass of the sun, most of those stars will make neutron stars. And this was something that was guessed by astronomers was going on soon after the discovery of the neutron in 1932 by Chadwick. And they guessed that you could make a star in which neutrons, which are like protons but have no charge, and so they don't have an electrical repulsion, and they can combine together to make a star that's held up by the pressure of the neutron. They figured this out, and they also guessed that it had something to do with cosmic rays. I'll return to that point. It was a marvelous inference that was made by 2 famous astronomers based on the nuclear physics discoverers that were going on. Again, you see this back and forth between astronomy and physics happening all the time. These neutron stars were actually first discovered by X-ray astronomers. Remember, we've now gotten the X-ray spectrum in 1962. They found the first example. And this was a neutron star that is orbiting a regular star. Mass falls onto the neutron star, and as it falls down, it releases a lot of gravitational energy. It gets hot. It does this through a disk of orbiting gas. Go here, and that was the first neutron star that were found, but they were really only recognized with this discovery by radio astronomers, typically Jocelyn Bell and Tony Hewish, the first discovery they made of what are called pulsars. And these are neutron stars with magnetic fields that make radio waves like a lighthouse swinging around like that. And radio astronomers see them. They're brilliant clocks. They go tick, 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 tick. And they're spinning magnetized neutron stars. So they have magnetic fields. And that gives you the lighthouse beam. There was more. Let me show you here. These neutron stars, once astronomers had realized, had said they really exist, physicists then got back involved in this, and they started using their nuclear physics to explore their properties, to make sophisticated descriptions of their interiors, and that's still going on, and we're still learning and learning and learning. And in fact, most of the physics that exists out there has some strange application to neutron stars. So people think about things like superconductivity or superfluids and so on. They're there inside neutron stars. They think about seismic waves. A geophysicist will think about seismic waves. You get the same thing inside a neutron star. So they're playground physicists for sure. Supernovae actually exist. Here's an image now of what you call supernova happened in the Magellanic Cloud in 1979. Sometimes these neutron stars orbit each other. Here are two neutron stars, a cartoon of them orbiting each other, so you can sometimes see both of the pulses from these neutron stars, and you can do wonderful experiments on relativity, and those neutron stars will eventually lose energy through creating gravitational waves, gravitational radiation. That's what the LIGO sees, but they lose energy, and eventually they will merge. And LIGO found one spectacular example of this, 2017, in August 2017, and I'll say a little bit more about that later. I mentioned the neutrinos. These are ghostly particles that hardly interact at all. They've got very, very weak interactions. And they were discovered first in nuclear reactors. They were theorized in the early 1930s, but they were discovered in nuclear reactors. But the sun, with its nuclear reactor, should be making neutrinos, and eventually those were discovered in a mine in Dakota, and these are the neutrinos which can be confidently calculated for the interior of the sun. Those neutrinos you can calculate using the principles of nuclear physics. And there was a big puzzle that came, and the puzzle was that the measurement was 1/3 predicted value. Oversimplifying slightly, but that was basically what was going on. And so some physicists said, you astronomers have done your calculations wrong. Some astronomers said the physics experiment was wrong. But it turned out both were right, because you may recall from about 4 slides back that there wasn't just one neutrino there were 3 of them. And the big discovery was that these neutrinos have tiny little masses. They're not like photons, have no mass. They have little masses, and through miracles of quantum mechanics and relativity, they are able to change from one form to another. So the sun was making electron neutrinos. Okay, very slow. Okay, I'll try and speed up. The sun was making electron neutrinos, and then they were changing into 3 types of neutrinos, and the detector was only detecting electrons. So again, that was a wonderful set of discoveries. Yeah. And nuclear astrophysics today, I've mentioned LIGO. This binary neutron star, sometimes called a kilonova, turns out to contribute the missing heavy elements that weren't made by the supernova explosion. About half of these heavy elements are made, and we now have a story of the periodic table of elements that looks like this. This is all the periodic table of elements, and we can partition the abundances of the elements that we see into this list of sources, including the emerging neutron stars and elements of the Big Bang, the dying stars, and so on. And we're also learning a lot more about the neutron stars themselves, and the interiors of them may not be just neutrons. They may be exotic combinations of those more elementary particles that I referred to at the start, about 7 lectures back. Things like quarks and so on, they may be present there, and this is something we can find out. And astronomers are able to measure the masses of these neutron stars, and we're learning a lot more about them through astronomical observation to answer the question of whether or not this is actually happening. All these exotic new particle physics happening inside the interiors of neutron stars. So finally, we're going to go next to the center of particle astrophysics. Huge amount has been discovered. I said there are cosmic rays. They were discovered over a century ago, well over a century ago, and then they were studied, and they were the source of particle physics. They were the particles of particle physics, were seen in, in cosmic rays that rain down on the Earth. And the positron, the positive electron, this is the antiparticle of the electron, the muon I mentioned, the pion, the kaon, I mentioned those as well. They were seen in cosmic rays. Nowadays, we have mighty particle accelerators, and they create these and many other particles that will. But historically, a lot of particle physics was begotten by cosmic ray physics. Here we got it here. That's what I showed you before. Furthermore, the cosmic rays themselves are interesting, and they have energies all the way ranging from modest things that come from the sun all the way up to energies that can be as large as 50 joules. And that's why I'll show again a picture of Tendulkar hitting a cricket ball. That's about the kinetic energy of a cricket ball. It's very hard, but hit really hard. And that is the energy of the most energetic cosmic rays measured on Earth. That's trying to understand them. Again, I'll return to that. We have seen gamma rays all the way up to the limit that we should see. The universe becomes opaque to gamma rays above an energy that's about a million times greater than those of the lowest energy cosmic rays and a million times less than the most energetic cosmic rays. You are seeing gamma rays all the way up there, and there are backgrounds here of gamma rays and X-rays and so on. Those are particles. Those are described by quantum mechanics. Our understanding of their source depends on quantum astrophysics. We talk about particle astrophysics today. Here's a picture of the premier gamma ray observatory now at the highest energy. This one is IceCube. It's one of the several neutrino telescopes. This one's in Antarctica and measures comparably energetic neutrinos. Obviously a terribly hard job because they're so weakly interacting. Here's a famous astronomical source called SS433. It was supposed to be just a binary star. It turns out to be a prodigious source of these highest energy particles, these highest energy gamma rays. That is amazing. Here are the neutrinos measured over the sky, their sources. And we're just starting to do neutrino astronomy. I won't claim there are constellations there, but there are sources that we're beginning to identify. I just want to have a slight interlude here for two purposes. One is just to talk about Hawking radiation. Now, everyone has heard of Stephen Hawking. I might also mention Professor Vishveshwara, because one of his early pieces of work, which Rajesh mentioned about, was to understand the stability of black holes. And he found that they were stable. Others had claimed this before, but he was the one who actually got it right. And that was a precondition for what Stephen Hawking realized, and others realized, was that black holes were capable of radiating. They weren't as black as all that. A small enough one would have a temperature associated with it, just like the sun has a temperature, and that means it can radiate photons, electromagnetic radiation. It can also radiate other particles. They're very small black holes, not like the ones that are in the newspapers. They're very small ones. There is no astronomical evidence that they exist, but as a source of physics, this very notion has, in the febrile imaginings of theoretical physicists, led to all sorts of investigation that have clarified and expanded our understanding of quantum mechanics, especially as it interfaces with gravity, the sort of gravity of Newton, if you like, or the gravity of Einstein and black holes. And where this is headed, and this was a big topic at the conference we attended, where this is headed is to say, don't just use the gravity of big black holes, let's use the gravity of very small black holes, where not just the photons have to be treated with quantum mechanical deference, the gravity itself has to be treated with quantum mechanical deference. And so, just like the electromagnetic radiation is made up out of photons, the gravity will be made up out of gravitons. And that fiery marriage between gravitons and photons is a subject called quantum gravity. It is very much a work in progress. There's been huge advances in understanding, but the theory is not yet with us. I hope that it will be one day soon. Moving on, I was asked to I didn't advertise this, but I'll say a few words about cosmology, and it is highly relevant to this story. Most of the description of the expanding universe has led to a standard model, just like that of particle physics, that is widely accepted. It is very simple. It is evolutionary. It starts from a very hot, highly dense condition. The universe expands, is still expanding. It has major constituents. Firstly, the visible matter. That's you and I, and stars, and all that sort of stuff. That's only 5%. There's about 27% that's a totally invisible form, or we call it dark matter, and no one knows what it is, and there's been extraordinary progress telling you what it isn't. So astronomers have used their methods, physicists have used their methods, both using detectors and so on, and so we have made enormous progress saying what it isn't and narrowing down the search, but when people try and identify this dark matter, the range of masses of the entities that are responsible go through 10 to the 95 between the lowest mass thing, that's something that's got a wavelength as big as a galaxy, to the highest mass thing, which will be something like a million solar mass black hole. So the huge range of masses there, but we're understanding a lot of that. The limits there, we know it exists through its gravity. And here's a famous example that one of my postdocs and helping make measurement, where we dark matter, blue, the gravitation effect, and then X-ray gas separated from it, an X-ray telescope, plus galaxies, and a very clear demonstration that dark matter is essentially only interacting through its gravity. We have also seen the measuring universe, particularly supernova explosion, but the biggest development has been using the radiation, called microwave background radiation, which is left over from the early universe, has a lot of energy associated with it. And here's a map of the whole site, Planck telescope, and by analyzing that, you can compare essentially a map, if you like, of the range of size, comparing theory. And here's theory, solid, then you can't see the error bar. The agreement between theory and measurement was. So we have a wonderful theory of cosmology, and we don't know what dark matter. And yet that is not even the worst embarrassment. The worst embarrassment is that most of the energy density of the current universe is something that Einstein called the cosmological constant. Nowadays it's called more generally dark energy. And that is just something we know is there. Describing its properties, we are even, we know its properties, describing its nature, we are not clear about at all. Again, I'll return to that perhaps at the end of it. So if we look at cosmology, the today. There's an awful lot going on that will help us understand these fundamentally quantum mechanical questions. What is dark matter? What is dark energy? Here's observations from a newly launched telescope that is in many ways best as the Hubble telescope or the Euclid telescope. More coming. Here's one coming called the Rubin telescope. That's Philly. That's me. In front of it, I just went to visit it first time. A month ago. And in front of it, they've been making measurements of galaxies, which is one of the ways that we can understand whether or not the fluctuations that you see in the sky, measured by the microwave background observation, radio telescope, evolve, as theory says, into the galaxies and collections of galaxies that we see around us today. There are more and more experiments being done to limit the amount of dark matter. One that's looking for a particular type of dark matter. Originally the experiments were like up there. Now we have upper limits there. This is experimental, very best. Before long they expect it down there. Here's a story told, the particle physics of the universe, and one of the big puzzles is why there's any regular matter there, because I said the matter had particles and antiparticles, and you might expect to be equal numbers of particles and antiparticles. They would combine together and cancel each other out. There should be no matter left over. Something strange happened in the early universe called baryogenesis, enabling us to have this meeting today. Otherwise, there wouldn't be any of us or anything. There wouldn't be any matter for chemistry or biology. And understanding the puzzle of that, it's called baryogenesis, again, an active line of research. No good answers, but lots of things can be ruled out. So this is just saying the particle physics, quantum mechanics, is stating the behavior of the universe. So how much time do I have left? Sorry? 10 minutes. Okay, I can easily do this in 10 minutes. So what I would like to do is, as advertised, having just given that brief summary of how the intersection, of astrophysics and physics has developed over the last century and how much discovery there has been. I just like to home in on three questions that are of interest to me, and I think they're astronomy questions, but they have a very strong and I think novel quantum mechanical component to ascension. The first, remember I showed you that spiral molecule in the interstellar medium that didn't look like its mirror image. So here's Tweedledum and Tweedledee. And I also said that we had cosmic rays hitting the Earth all the time. One of those things that those cosmic rays do is they create these particles that I drew attention to, muons, as discovered in cosmic rays, muons. And in fact, there'll be one muon going through your body about every few milliseconds, even on Earth. They're the dominant force of cosmic rays on the surface of the Earth. Now, those muons themselves have a property associated with their magnet, little magnets associated with one, and that makes them spiral. So the question trying to answer, why, when you look at biology, look at living substances, there is a choice made by the DNA, by complex protons, by all that happens in a living body. It is one hand and not the other hand, left side or right side, and that choice is one of two choices. And everywhere we've looked, sample returns, perhaps, certainly digging down in vents and volcanoes and so on, we see this one choice that's been made. It could be just an accident, but it could also be an expression of interaction of muons with their handedness assembling molecules as they're making reactions, failing almost all the time to make long chain DNA and so on. And so we are theorizing that there is actually a causal connection. The reason why we have DNA that twists one way and not the other way is ultimately related to the same character of the gluon that are hitting. Interact molecules in bond, so on. And so we've been doing theoretical work, but also experimental work. This is how we're gluon experiments, well, taking gluons made on Earth and exposing biological materials to them. So that's one topic that we're interested in. And one thing I'm personally quite convinced of is if this is relevant, and I'm not claiming that it is, evidence that there is as yet, then quantum mechanics front and center in a new way to explaining this. Go to my second application, and that was the neutron stars. I said they were magnetized. The magnetic fields were impressively strong. They were several trillion times larger, typically, than the Earth's magnetic field, maybe 10 billion times larger than the magnetic field that might be attached to a refrigerator. That's very strong magnetic field. You can't sustain that on the Earth. But it turns out there are now neutron stars with magnetic fields that are yet 1,000 times larger. From a physics perspective, this takes us into completely new territory. Because what it says is that any matter under those conditions is so dominated by the magnetic field, and the states in which the electrons can exist are so large apart that they'll just make electrons and positrons freely and clearly. And we have to take the theory of quantum electrodynamics, normal description of electrons and positrons and everything else in magnetic fields. We have to take it into a completely new regime. This happens in magnetars. So, schematic of the way that we think about this. These magnetars are observed as X-ray sources. They're also observed as radio sources, called fast radio bursts. You may have heard of them. They happen at a rate of about one a minute or so over the whole sky. They're now being studied extensively by radio astronomers. And the most popular theory, and one that I've always subscribed to, is that they are magnetic flares made on magnetars. That's a neutron star. A neutron star is a star that has the density of the nucleus and a size of about 10 kilometers, about 10 kilometers in radius. There's a lot of exotic physics that goes on there. It's shown schematically here. I need a large collaboration that is spending a lot of effort into understanding all the processes that work. And there are also experiments that are being done using lasers that can mimic some of the physics that is relevant in this new regime for quantum mechanics. So this is an exciting development. And then finally, I'll go back to the cosmic rays. I said the highest energy particles that we have the energy of a well-hit cricket ball, much more energetic than we can make, or even study with our best particle accelerators, 100 times more energetic in the relevant terms. And there are much speculation as to how the universe creates these particles. We know a lot about the problem. We know what mechanisms that can't work. And I believe that the three remaining candidates are, one, that the shock fronts created by giant flows in intergalactic space accelerate particles and are capable of accelerating them to these energies. Second is things like the magnetars in their earliest days could make them, or perhaps black holes could make them. And the third is that outflowing jets of gas moving at relativistic speed, perhaps associated with galaxies, perhaps associated with exploding supernova-like stars, they can also make. These are three classes of explanation. And the way forward is to be able to take an individual highest energy cosmic ray, which we think is an iron nucleus, but we're not sure, something like an iron nucleus, but we're not sure. It hits the Earth. Every one that comes, we want to be able to measure where it came from, what its energy is, and what its composition is. Is it iron, or is it a proton? So far, all the evidence is that it's something like iron, but we're not sure. We're starting to be able to do that. Already, you've been able to see the sky is not isotropic. There's about a 10% variation, one direction to another direction, but we're not at the level where we can identify sources. There are additional complications to entertain. So this is the challenge ahead, and the challenge to quantum mechanics is the people who use the giant particle accelerators, like the Large Hadron Collider, to be able to help us to make better models of these stars here, so we can infer those three quantities: composition, direction, and energy. As soon as that can be done, then we can tell which are any of these are correct. So that's science in progress, and it is going to require new techniques applied to understanding quantum mechanics of these shafts. I think that's my last slide. Let me just, oh yes, I was just going to say something here. So I'm just allowed 2 minutes, just make one point. I want to come back. And I think this is a sort of theme future. One of the things of quantum mechanics has done, with its emphasis on the very small, has to produce a sort of mindset that physics, the world around us, is dictated by the small. So think about the small, and then we think about the not so small, and then the not so small, and not so small, and build up large scale. This is a process sometimes called reductionism. So you say, what's an atom made of? It's behind electrons, or the nucleus made of quarks and gluons, blah, 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 and you keep on going. That is a perfectly legitimate way to approach, but it may not be the practical way. Here's an analogy. Tsunami, if you think about it the right way, is about the same temperature, about 10 to the power 40 degrees Kelvin, gamma ray burst, as a radio burst. Tsunami, if you ask an oceanographer, how do you describe a tsunami, they would say, I use equations of hydrodynamics. I just treat water as a fluid. I don't consider it as being made up out of water molecules. So it's top down rather than bottom up. We don't know what dark energy is. Normal way, think about it in this reductionist way, is to think about it as essentially a quantum mechanical structure, a result of this theory of quantum gravity that we don't yet have, but it's something that's built up and understood from the smallest scale to the scale of the universe. Just let me throw out there a speculation that this might be wrong, and maybe just like the atoms and the electrons and nuclei and so on, and the photons, for the first glimpse of physics, the quantum physics of the small scale, maybe dark energy is an expression of the physics of the very largest scale beyond the size of our observable universe, taking us way out to large distance. And so that too, like oceanography, is in practice thought about most usefully as being the physics of the very large, reduced to small, rather than the other way around. I leave you with that thought. I thank you for listening, and thank you very much for your kind invitation to come and give this lecture.
Thank you, Professor Blandford, for this wonderful quantum journey through the cosmos. He will be willing to take a few questions. So if you have a question, please raise your hand. One of our volunteers will bring a mic to you. Okay, the young person here. Maybe they. Okay, start from here.
First of all, thank you, Professor, for the wonderful presentation and the talk. Mine is like a very vague question, I would say. So we were talking about particles, standard model of particles and many particles. So my question is, what do you think a particle is? Because I cannot say it's a concentration of mass. Again, photon doesn't have a mass. So what is a particle according to you?
Well, there are particles and particles. If I talk about a speck of dust, I could say from some perspectives that's a particle. Somebody would say that, but then I know it. You and I know it's made out of molecules, and then those molecules are made up out of atoms, and those atoms are made up out of electrons, and there are fundamental particles. And to me, that particle is something that you say, what's an electron then? Electron, to someone from the 19th century, they would say that's essentially a point, and then they would say, well, that's a point that has structure, and that's what started to get them into trouble. And it was really one of the motivators, the quantum description of the world around us, to say it is really what we call a field. So we can think about it as having a localized form. It has a wave function, of course, in an atom. And so it isn't just this sort of indivisible point. It really has that structure. Now, if you want to go beyond that, you've got to get into quantum electrodynamics and quantum field theory, particularly quantum field theory, and ultimately, I suppose, you have to go into quantum gravity. But if you talk about it operationally, most of my work is nowadays done in plasma physics. For me, it's just that indivisible point. I know that underneath it, something is much more interesting and structured, but it's not relevant to what I actually do on a daily basis. So it really depends where you're coming from, how you answer the question.
When you see the rectangle with colors,
Oh, yes.
how do you know which black line is for which element?
Oh, from its wavelength. So what astronomers did in the 19th century was they measured the wavelengths at which you saw those that they were originally called Fraunhofer line, and they measured the wavelengths, and they found that certain stars had the same wavelengths appearing. I might mention parenthetically that doing this form of what's called spectroscopy led to the discovery of helium. People until in 1868, and the observation it's associated with usually associated with something called Lockyer, but the observations were done in India.
Hi, sir. I just want to ask about the implications of quantum mechanics on biology. So, what could be the possibly, undiscovered relation between quantum mechanics and how it's impacting our biology, right? In the book What is Life, Erwin Schrödinger mentioned briefly. But if you can talk about, are there yet to be made discoveries on this topic? So that will be very helpful.
The quantum mechanics has to be a part of biology. I mean, everything is part of everything in some sense, so it has to be part there. I think the question you're asking is one that was raised by one of the participants at the meeting. We ought to be talking more about the very question you asked. Sometimes this is dismissed by, people say the ghost in the machine or something like that. People are sometimes a bit dismissive of this, but my own view is that quantum mechanics is in some way essential in a way that's different from just biological molecule collection, the regular atoms, the carbon, there's oxygen, there's phosphorus and hydrogen and so on. it's more than that. There are things going on there that involve quantum mechanics in new ways. It is not necessarily mystical, but I think it's important. And my own speculation is that it may be one of the means of an explanation for how some forms of life might develop, for example, on the early Earth, perhaps example on other exoplanets. We don't know whether life is just unique to Earth or ubiquitous throughout the universe. I'm just flying off on a bit of a tangent here, but I'll come back to your question. When I was a student, my boss, Fred Hoyle, was a great believer in and exponent of what's called panspermia, an idea going back to the Greeks, that there is life everywhere. And I think most of us would not have taken it terribly seriously at that time. But what astronomers have discovered is that our solar system is not, essentially, most stars have planetary systems around them. And these are riotous places. They're a bit like Bangalore traffic. And there are big trucks and small scooters. And the small scooters don't do so well. They very quickly get kicked out into interstellar space. And just an occasional one may carry some primitive form of life, a prion or something. And I did think about this. I read, in fact, you may have heard sort of semi-humorous books by Douglas Adams called The Hitchhiker's Guide to the Universe. I wrote a paper once called The Guide to the Hitchhiker's Universe. So the notion was that inside these rocks might be dormant living form that propagated life from one planetary system to another, all the way through the galaxy and in principle, into neighboring galaxies. That's the extreme view of panspermia. The other extreme view is that we're only here, it's just us here, and it's such a rare thing to happen, and we, self-definingly, we're the only life in the universe. That's the other extreme view. I don't know which is right. Maybe I think it's one of the big questions is to identify with honesty and understanding conditions for life to develop and or be present in other exoplanets. That's what we'd like to do. So having said that, let me return to your question and say, if the panspermia is closer to the truth, at least in the sense there's lots of life out there, then we're not just worried, not just thinking about making my colleague Ajit in some way or making him function. We have a much larger problem to entertain. And thinking, and I have to believe that quantum mechanics is part of the story.
Sir, I do have one question regarding dark matter. When we are discussing about dark matter,
only one question regarding.
I have a lot of questions regarding dark matter.
Yes.
But still, we know that dark matter does not interact electromagnetically, which makes them invisible to our eyes. They only interact through
As
gravity.
far as we can tell, yes, because people have tried very hard to measure very weak interaction.
But
there's nothing convincing as yet.
But does that mean dark matter necessarily associates with matter? Only in the presence of matter, dark matter exists. Or dark matter, is there any dark matter source that exists without any matter? Visible matter.
What we the standard model of cosmology says that in the earliest time, the dark matter and the so-called baryon, that's the regular matter, were pretty well mixed. And there were fluctuations. Those fluctuations, I dropped this out, but I'll say it now. Those fluctuations have a quantum mechanical origin that is rather similar to the process that Stephen Hawking identified around black holes. The early universe arises just like a black hole. That's a parenthetic remark. So we have initially fluctuations in dark matter, and in the baryonic matter. And then what happens later in the universe is the baryonic matter, the stuff of you and I, much more friendly and interactive and makes photons cool and make atoms and so on. And that will collapse and separate the dark matter. So if we look at a galaxy like ours or Andromeda, it's much bigger in dark matter. It may be 10 times bigger in dark matter than what is shining in stars. And so you've already separated it. Now, if you say, is there some place in the universe that only has was made only with dark matter, with no regular matter, then most cosmologists, including myself, would say for that to happen would be so counter to our understanding of the conditions in the early universe that has been so successful in giving us a standard model which has survived all manner of people trying to prove it wrong. They failed. That's the way science goes.
Thank you, sir.
Good evening, Professor. So my question is on how much the idea of quantum gravity.
Yeah.
So
I'm sorry.
so my
I need a
question.
chain. Oh, okay. I've got this. Okay, I can wander around.
Okay, so my question is on how much the idea of quantum gravity has evolved and how close we are to getting a unified field theory.
I think the answer I have to say is Rajesh will give you an answer tomorrow morning. He has worked on problems like this. And I don't know. I'm not clever enough to work on the deepest theoretical physics, but I am an observer of people who work on deep theoretical physics. And when they make great advances, it's usually a bit of a surprise. There was a time when string theory came out of it, was sort of hovering around there. Then all of a sudden, around about the 90s, a lot of clever people put together a theory that looked awfully promising. It still has a lot of appeal and promise, but it has not yet been able to make the contact with experiment and observation in a direct way, a compelling way, that people at that time had hoped. But so, you know, there are theories of quantum gravity. There are, I probably get 2 a day on my email. But in terms of things that really are compelling in the way that the theory of general relativity, or the theory that we're celebrating 100 years ago of what became, you know, quantum mechanics, that is not yet here, but it could happen. It could happen very, very soon, or it may not happen before ICTS has a celebration of the second centenary of quantum mechanics. Well, I look forward to meeting all of you.
Could we take one question? The online audience, we have a large number of
Please,
online
yeah,
audience.
oh yes,
So,
please do.
So one question is, would black holes grow in their size over cosmic time?
Oh, black holes, yes, black holes grow. They can shrink, but the only ones that shrink are the very, very small ones that are radiating. If they radiate, they lose energy, they lose mass. Remember, E equals mc squared, so they lose mass, and that means they shrink. But when I say that, they only shrink in the brains of theoretical physicists, because we have no direct observations of these structures as yet. Nothing that small has been seen. And they've been searched. I mean, I've been involved in searches for them, but all we've got is upper limits. It's like dark matter. Now, the big black holes that we've got abundant evidence for are stellar size, and of sizes up to now 25 billion times the mass of the sun. Those big black holes grew, and they grew from accreting gas. The famous one in M87, remember the great big orange ring that was all over the newspapers, the famous one in M87, that has a black hole mass of about 6.5 billion times the mass of the sun. It's now being fed. It's got a very bad mother. It's not being fed well at all. But in the past, it was fed a lot, and it would have been probably the brightest star in the sky, as bright as Vega at that time. Now it is rather pathetic. It's being starved by its mean galaxy. And so, but it's still growing, but very, very slowly. So when we see the mighty quasars in the early universe, those are the black holes that are growing very fast. They're growing, and their masses are increasing on timescales of 10 or 100 million 10 or 100 million years.
You said before that stars are powered by nuclear fusion. So is there a possible way we can get fusion to Earth and, you know, make it an energy source? And for doing that, what are the necessary technology that we need to develop? Thank you.
Well, amongst the many emails I've received over the years with helpful suggestions was one, all you got to do is make gravity stronger. So that's one answer I can give you, but I'll have to refer you to another authority. No, to be more serious, fusion has been proposed for a very long time, the 1930s, as a potential source of power in terrestrial reactors. It's a terribly hard problem to do. There are basically two classes of devices that have been proposed. One of the ones are things called tokamaks, or also things called stellarators, and there are things that look like that, where the hot plasma with temperatures of 100 million degrees, even hotter than the center of the sun, are held together by strong magnetic fields on Earth. The other uses lasers. I showed a picture of laser experiments where you have beams of lasers that come in that case, in 192 different directions onto a tiny pellet and crushes it. And you can make fusion work in that case too, in principle. Now, in both of those approaches, there have been considerable physics achievements of late. And that has encouraged, around the world, I think, much more interest and indeed investment in these technologies. But it's still going to be a long time off before you have commercial reactors. In my view, even if you can get the physics to be plausible, you've got a huge number of engineering problems to solve. And the engineering is a major challenge in these problems. This is to say it's insuperable, but to make fission reactors, the ones that people in India and elsewhere have, are fission reactors, and that's looking at the heavy elements like uranium, breaking them down towards iron, and releasing energy that way. Those work, those have been operated, but they didn't happen easily. It was a lot of engineering to make those into sources, genuine sources of power. And so the comparable amount of engineering will have to happen for the fusion reactors. How long it's going to take, I don't know. Which of the approaches that are being, now many more that are being explored at the moment, is going to be the most useful one, again, I don't really know. But I am confident that people will continue to work on this problem, and there will be investment in it because there's a strong need for alternative sources of power. But how long it takes, I mean, when I was young, it was going to be, well, it was going to come very soon, actually, when I was young, and then they realized it was a harder problem. Then it took 50 years. I don't know whether it's going to take that long now. My guess is there will be fusion reactors at some point, but how long, I can't say.
Hello.
Okay, let's have this the last question.
Yeah, in one of the previous slides, you had mentioned something about ludicity.
Oh, gosh, you're the second person to catch that. I made up, I always say, well, you don't know what audacity is. I made it up. It's a word I made up. Okay, I'll explain. So thank you for catching that. There's a thing that's sometimes called helicity, which is for a particle, and it tells you whether or not the direction in which it is going is the same direction as the direction in which it is spinning. Now, particles like muons are charged, and when they spin, they also have magnets associated with them. And the quantity we were interested in is the comparison of the direction in which they're going and the direction of the magnet, not the direction of the spin, because that depends on the sign of the charge. And so that's why we distinguished lodacity from helicity, which is what they normally use. So it's a word that I made up, and I apologize.
Okay, I think this is a good time to stop. I know there are many more questions, but unfortunately, every good thing has to end. So let's thank Professor Blandford for this wonderful lecture.
Thank you very much. Thank you for your good question, for your excellent questions.
So we have a few logistical announcements. There is a bus going back to Majestic after the event, so feel free to take that. And we also have other refreshments available, so if you want, you're welcome to take the back home. There are also buses going back to IISc and ICTS, so feel free to take them if you are going that way. So before you leave, please stay for a minute. So we know that this event has been hosted by the Christ University. In particular, our colleagues from the Center for Astronomy and Astrophysics has been playing a pivotal role in hosting this. Let me ask my colleague, Professor Pleasant Matthew, to make the final concluding remarks.
Hello, good evening, everyone. I know it's a long evening. I'll keep it very brief. So on behalf of Christ University, Management, Department of Physics and all, I would like to extend our thanks to Professor Roger Blandford for giving this wonderful talk. And before this, he interacted with students, all these future astrophysicists and all, and it was a great session. Thank you very much, sir. So then my thanks to the leadership of ICTS, Director, Dean, and the coordinator, Disha, all these people for making this event here, for conducting this event here. This is really good. I mean, and we should keep on doing this collaboration in future. Thank you very much to ICTS. Also, I would like to thank our technical team. I mean, today is a holiday, by the way. I mean, but then they are working in a whole day evening. Thanks to the team, also from the ICTS team, for getting this event done. Thank you very much. And thanks to all of you for coming here to Christ. Keep coming again to Christ. We would love to host you here. Have a great evening. Thank you very much.